Hi everybody, this is Mr. V. Hill, and today I'm going to be talking to you about solving systems of linear equations. Specifically, we're going to be talking about what is called the elimination method. Okay. But first, before we get to that, let's review just a little bit of what we've already covered. So first, we're going to review solving by graphing and the substitution method. So let's just go over one quick little example here. Call it example 1. System is going to be y is equal to, say, 3x minus 2, and the other one will be y is equal to negative 2x, I don't know, plus 8. That sounds good. Okay. So the whole idea here is that we have two linear equations. Kind of nice. Here they are both in slope-intercept form. Here we have a slope of 3, y-intercept of course, negative 2, because of subtraction. And here we have y is equal, well, here's the slope of this line, negative 2, and the y-intercept is 8. So it's going to be pretty easy to just graph these things and then kind of try to see where the point of intersection is, because that's what solving a system really means, is we're finding the point of intersection for these two sets of points. So first, graphing. And I'm just going to do this kind of rough sketch like. Of course, you'd want to use graph paper, but I think we can get the idea here. There's x-axis, y-axis. So the first line is going to have a y-intercept of negative 2, down 2, and the slope is going to be 3, so we'll go rise 3, run 1. There's 1 point, here's another point. If we want to be a little bit more accurate, we could of course rise another 3 and then run another 1. And got a point there, and now we kind of see that our first line looks something like that. Okay, now let's plot the other line. Of course, here we've got a y-intercept of 8, so we got, let's see here, 1, 2, 3, 4, 5, 6, 7, 8. There's the y-intercept. And now we're going to follow a slope, of negative 2, down 2 to the right 1. Oh, what the heck, let's go another one. 1, 2, to the right 1. Oh, hey, I think that was a point on our other line too. Kind of nice. Things worked out pretty smoothly for us here. Of course, not always going to be the case. So here's the line, y is equal to negative 2x plus 8. So we're saying that the point of intersection, it sure looks like, according to our graph, the point of intersection is at 2, 4. Cool. We just solved it. But let's check to make sure we actually did this correctly. So we should check by plugging this point back into both of our original equations and see if we get a true statement out. Because that's kind of how this whole thing works, right? If we plug in the coordinates to our equation and we get a true statement, then yes, this point is on that line. Same thing with the second one, and we're really trying to figure out if this point is on both lines, what it means to be the point of intersection. So we'll plug in our y-coordinate here, and we ask ourselves, is that 4 actually equal to 3 times our x-coordinate of 2 minus 2, let's see here, 4 equals 3 times 2 is 6, minus 2, that's 4. Yeah, absolutely. But we've got to check the other equation as well. So we plug in our y-coordinate of 4 right here, and we ask ourselves, is that actually equal to what we get when we do negative 2 times our x-coordinate of 2 plus 8. And yeah, negative 2 times 2 is negative 4, add another 8, yep, we sure get 4. And of course the whole set notation thing, which I'm not all that excited about, or I don't really push it, but here we go. The set notation would be that the solution set to this system of equations is equal to the set of the 1 point, 2, 4. Okay. And there would be your solution. And that's solving by graphing. Of course, it's not always going to work out so nice if these coordinates of the intersection point aren't nice integers or even rational numbers. So let's try our other method of substitution. And so with substitution, what we're going to do, y is equal to 3x minus 2, and y is equal to negative 2x plus 8. Whole idea here is we're going to substitute this other name for y into this second equation. And of course, it doesn't matter where you go. You can, if you have it solved for x, you can substitute in the other name for x. It doesn't really matter. But what happens here is that this system of two equations in two unknowns now all of a sudden becomes 3x minus 2 is equal to negative 2x plus 8. And now we have a single equation in a single unknown. That's kind of important, right? Because, well, we already know how to solve a single equation in a single unknown, at least a linear equation, which this, of course, is. No big deal. But if you really want to think about it in a weird way, up here we have two equations, but big important part, we have two variables, an x and a y, which means what we're really talking about are points in this two-dimensional space of the coordinate plane. Now, when we do the substitution, we end up with a single equation in a single variable. One variable means we're now not in a plane, we're just on a line, the real number line. So what you can kind of think of is the substitution, what it does is it takes this two-dimensional coordinate plane and it's kind of like a trash compactor. It just smashes everything down to the x-axis, because now we only have the x variable here. You could, of course, smash it this way and collapse it to the y-axis, which is what you would do if you solved one of these equations for x and substituted that into the other one. So either way it works, but that's the idea. So we smash this coordinate plane down to the x-axis, and of course this point is going to be smashed right to there, or where x equals 2. Let's see what happens when we solve this equation over here. Of course, we need to combine the like terms first before we can start undoing what's being done to the variable x. So we're going to add 2x to both sides, giving us, of course, 3x plus 2x gives us 5x, still with our minus 2, is equal to. Now, the whole point of this was to get rid of these x's on this side. Negative 2x plus 2x is 0, so we just have 8 on the right. And now all we have to do is now undo what's being done to x in order to solve for x. So we will, instead of, and if we really want to, we can always look at this as, of course, back to these darn things that you hate. The operations being done to x on this side and the inverse operations on the right. Well, the first thing being done to x is multiplying it by 5. The exact opposite of multiplying something by 5 is, of course, dividing by 5. After we multiply x by 5, then we subtract 2. And the exact opposite of subtracting 2 is adding 2. So to undo what's being done to x, we're going to apply these inverse operations in reverse order. Whole socks and shoes analogy, right? You put on your socks, then you put on your shoes. To undo that, you've got to take off your shoes first, and then take off your socks. So we're going to add 2 to both sides. Point being that subtracting 2 and adding 2 cancel each other out. 5x is now equal to 10. So we've taken off our shoes. Now let's take off our socks. We're going to divide both sides by 5. So we can get rid of those. And now x is equal to 2. Oh, hey, yeah, and that's exactly what the coordinate of the point of intersection was over here. So there's half of our solution. We get the other half just by plugging this value for x back into, well, either equation, really. Really, if you want to check it, make sure you're absolutely correct, just plug it into both equations. Make sure you get the same thing. So plugging this into the first equation, well, y is now going to be equal to 3 times 2 minus 2. 2 times 2 is 6, minus 2 is 4, so y equals 4. Let's try the other equation too, just to make sure. Y is equal to negative 2 times 2, right, and 2 times 2, plug our x coordinate in, plus 8. And now y is equal to negative 2 times 2 is negative 4, plus 8 is 4. Fantastic. Got the exact same answer. Good. So that was graphing and the substitution method. Now what we're going to do is we're going to move on to our new method called the elimination method. And we'll just use this exact same example. We have y is equal to 3x minus 2, and y is equal to negative 2x plus 8. There's our system. Now here's how the elimination method works. This thing is equal to this thing, and this thing is equal to this thing. So if we add these two things together, we should get the exact same thing as what we get when we add these two things together. Okay? Simple example, or another way of saying this. Suppose you get two people, right? Fred Jones, perhaps, and Sally Smith. What the heck? Okay? So what we're saying is, this guy Fred, he's got another name. Mr. Jones. But also, Sally has another name, Ms. Smith. So Fred is the same thing as Mr. Jones, and Sally is the same thing as Ms. Smith. So what we're seeing here now is that Fred and Sally, what we get when we put these two things together, is exactly the same thing as Mr. Jones and Ms. Smith. Right? That's basically what we're going to do here. However, the way we want to do this is we got to do this kind of smart so that we still want to break these two equations in two variables down to one equation in one variable. Okay? So what we're going to do is we're going to eliminate one of the variables. Okay. We could do this now, of course. We could subtract one equation from the other one, or we can add the two equations together. Of course, subtraction is the same thing as addition, just adding the negative of the next thing. But, so I hate subtraction. You lose negative signs all over the place when you try to do it. So, if we add these two equations together as is, well, y plus y is 2y, 3x's plus negative 2x, that nothing gets eliminated. So what we're going to do, we're just going to make it so an elimination will happen. So we're going to multiply both sides of this equation by negative 1. Okay. Now, of course, remember you're multiplying the entire side of the equation by that negative 1, so we are going to have to apply the distributive property. It's really, really easy to forget that. I've done it a million times myself. But so now what we got, we're going to rewrite our system. And now we have y is equal to 3x minus 2. And now we've got negative 1 times y is negative y. We distribute in negative 1 times the negative 2x is positive 2x. and negative 1 times 8 is negative 8. And again, like I said, I absolutely despise subtractions because it's too darn easy to lose a negative sign. So I'm going to switch this subtracting 2 to adding negative 2. In my opinion, always a good idea. So here's our new system. But it's not really a new system, it's the exact same system, it's just written a slightly different way. But now what we do is we're just going to add the two equations together. Well, really we're going to add the left-hand sides of the equations, and we're going to add the right-hand sides of the equations. Really what you want to do is you want to just basically, they need to be in the same form, or really what you need is just the y's on top of the y's, the x's on top of the x's, and the constants on top of the constants. And then when we're doing this, we really get to combine the like terms all at the same time. So y plus negative y, that's of course just 0. Notice we've eliminated the y's now. 3x plus 2x gives us 5x. Plus negative 2 plus negative 8 is negative 10. And now what we have is a single equation and a single unknown x. Okay. But we might want to look back at what we did with the substitution method and notice that at some point along in here, what we ended up with was this equation right here. 5x is equal to 10. And that's really what happened when we did our substitution and then we combined all of the like terms. We combined the 3x and then negative 2x here on this left hand side to give us 5x. Then we really combined the constants over here to give us 10. And if you look at it, well, this equation right here is the exact same thing as this equation right here. All we need to do is subtract 10 from both sides, and we've got it. So really all the elimination method is a shortcut for the substitution method and combining the like terms. That's all it is. But people tend to like shortcuts, so that's that. But now, again, all we've got to do is solve for x now in our single equation with just the unknown x. Of course, we're going to undo this adding negative 10 by adding 10 to both sides. Get rid of those. And now we have 10 is equal to 5x. Of course, we undo this multiplying by 5 by dividing both sides by 5. Then we simplify, and of course 10 divided by 5 is 2, and that equals x. Half of our solution. And of course now we're going to get the other half of our solution by plugging this x variable back into both of the original equations. And of course, well, we've already done that before, and so y is equal to 3 times 2 minus 2, and of course, yes, y is equal to 4 for the first equation. For the second equation, y is equal to negative 2 times x, but x is now 2 plus 8, and of course then y is equal to negative 2 times 2 is negative 4 plus 8 is 4. So again, we get the exact same solution set, which consists of the point with coordinates 2, 4. And there is the final solution. Okay, that's the elimination method, basically. But of course, it's not always going to be quite so simple. Let's try a second example. This one will be example 2. Let's see here. Let's maybe do 3x minus 4y is equal to 14. Sure. Maybe 2x plus 2y equals, oh, I don't know, maybe 21. Sure. Okay. Now, these are in standard form as opposed to slope-intercept form. I mean, we could still solve by graphing, we could still do substitution, we could do all of that, but this when both are in standard form, it's really set up perfectly for elimination. But you just got to now think about this a little bit. If we were to add the left-hand sides and the right-hand sides together, see, we're not going to get any elimination here. 3x plus 2x, that's 5x. Negative 4y plus 2y, still negative 2y. We don't get rid of either of the variables. But if we notice here, 2 and 4. Really, we've got negative 4 here. And again, I hate subtraction, so let's switch that to adding negative 4y. Now we got a coefficient of y of negative 4 up here, 2 down here. But if we multiplied both sides of this equation by 2, then we would have 4y, and then when we added negative 4y to 4y, we'd get rid of the y's. So what we're going to do is multiply both sides of this second equation by 2. And again, don't forget that you're multiplying the entire side of the equation by 2. So you are going to have to apply the distributive property. So let's rewrite this system. 3x plus negative 4y is equal to 14. Now we've got 2 times 2x, which is 4x, plus 2 times 2y, 4y, is equal to 21 times 2, which is, of course, 42. And now we can take this system and add the left-hand sides together and the right-hand sides together. On the left-hand sides, well, we're going to combine the like terms of the x's. 3x plus 4x is 7x. But now, beautiful, negative 4y plus 4y, that equals 0. So now this is equal to 14 plus 42. We're adding the right-hand sides together as well, and that's just 56. Again, now we have our single equation and the single unknown of x. Very easy to solve this now. Divide both sides by 7. So those will cancel out. And now we have x is equal to 56 divided by 7, which is, of course, 8. So that's half of our solution. We're going to get the other half of our solution, meaning the y-coordinate, by plugging this value for x back into either equation up here. We're actually going to do both, just to make sure we did this correctly. So let's first plug it in the first equation. 3 times our x-coordinate, which is 8, plus negative 4 times y is equal to 14. So now we just got to figure out what y is. So we'll just solve this. 3 times 8 is, of course, 24. Let's rewrite this. Now we're going to undo what's being done to y, but in reverse order. So first thing we're going to do is subtract 24 from both sides. Negative 4y is equal to 14 minus 24 is a negative 10. Then we've got to undo this multiplying by negative 4. And we get y is equal to, well, these negatives are going to cancel out. 10 divided by 4, that's 5 halves. Okay. So here what we're saying is the solution set, or the point of intersection, here is just going to be the point with x-coordinate 8 and the y-coordinate of 5 halves. But just to make sure, we should really check the other equation too. So we'll plug this back into the second equation and see if we get the same y value. So it was 2 times the x-coordinate of 8 plus 2y is equal to 21. Of course, 16 plus 2y is equal to 21. Subtract 16 from both sides. 2y is equal to 5. And yes, of course, when we divide both sides by 2, again, our y is 5/2. Of course, what you could have done is just taken this 8 and 5/2, plugged them back up here, see if you get a true statement. Which you would, of course. 2 times 8 is 16, 2 times 5/2 is 5, 16 plus 5 is, of course, 21. No big deal. Okay. Let's try one more example. This one will be a little bit more complicated. Example 3. Let's try this. 5x minus 6y is equal to 12, and a 3x is equal to 5y plus 24. So here's our third example. One difficulty here is that, notice the equations are not in the same form. This guy's in standard form, this guy's in something that is not even a named form. But really easy to deal with. All you gotta do is write this one in standard form and then you're done. And that's so simple. All you gotta do is kind of, there's no teleportation, but we gotta move the y stuff over to the left. We're going to do that by subtracting 5y from both sides of the equation. And so we're going to rewrite the whole thing. This is, of course, going to cancel out. And our system is now 5x minus 6y is equal to 12. And then 3x minus 5y is equal to just 24. Same system, just written a little bit differently. Okay, but again, I cannot stand subtractions, so I'm going to change both of these to adding the negative of the next term. But now again, if we look at this, when we add the left-hand sides together and the right-hand sides together, we're not going to get any elimination. 5x plus 3x is 8x, negative 6y plus negative 5y, negative 11y. We don't get rid of anything. But let's think through a little bit. 5 and 3. All you gotta do is, and you can do this with either variable, it does not matter. But here we're just gonna multiply both sides, both equations by something so that we will get some elimination. So if we multiply this top equation here, multiply that by 3 on both sides, and we multiply the bottom equation, both sides, by negative 5, well, what's going to happen? 3 times 5x is 15x, negative 5 times 3x is negative 15x. So 15x plus negative 15x, those are going to go away. Of course, don't forget that you're multiplying the entire side of the equation. So you are going to have to apply the distributive property. You could have done the same thing to get rid of the y's. Now we had negative 6 and negative 5. If you multiplied, say, this guy by 5 and this guy by negative 6, then we're going to be able to get rid of those. So you just got to think about it a little bit. So let's rewrite this now. 3 times 5x is 15x plus 3 times negative 6y is negative 18y. On the right hand side we've got 12 times 3, which is 36. Second equation, negative 5 times 3x is negative 15x plus negative 5 times negative 5y is going to be a positive 25y. And 24 times negative 5 is, what is that, negative 120. Okay. Now we're going to get some elimination when we add the two equations together, or really add these left-hand sides together and these right-hand sides together. because 15x plus negative 15x, those are just going to go away. Now we've got negative 18y plus 25y, which is going to be, what is that, 7y? And 36 plus negative 120 on the right-hand side gives us, I think that's negative 84. So now, by adding the two equations together, we've eliminated the x's. Now we've got a single equation and a single unknown, but this time y. Which is totally fine, no big deal. Kind of like trash compacting it, the whole coordinate plane towards the y-axis instead of the x. But now we just solve for y, divide both sides by 7. Of course, these are going to cancel out. And now we've got y is equal to negative 84 divided by 7 is, of course, negative 12. And that's half of our solution. The y-coordinate of the point of intersection. Now you just got to go back and figure out what the x-coordinate is. So we just plug this back into this equation. So we have 5x minus 6 times our y-coordinate now of negative 12. That's supposed to equal 12. Or 5x minus 6 times negative 12 is a negative 72. So let's just write that as plus 72. Right? Because I hate subtractions. And now we just solve for x now. We subtract 72 from both sides, because that's going to cancel out now. 5x is equal to 12 minus 72, which is a negative 60. Now we divide both sides by 5. So that those will go away. And now we have x is equal to negative 12. Okay. So what we're saying here is this is the x-coordinate of our point of intersection. Here's the y-coordinate of the point of intersection. So the solution set to the system is the set of the point negative 12, negative 12. But of course, we probably do want to check the other equation as well, the second one, just to make sure. So what we'll do here, we'll just ask ourselves, well, do we get a true statement out when we plug in these coordinates? You could, of course, just go back and plug in negative 12 for y and then solve for x, see if you get the same thing. But this works out too. So we're going to check the other equation. And ask ourselves, 3 times the x-coordinate of negative 12, is that actually equal to 5 times the y-coordinate of negative 12, and just plug in our y-coordinate there, plus 24. Or we're asking ourselves, is it true that, well, 3 times negative 12 is negative 36? Is that actually equal to 5 times negative 12 is negative 60 plus 24? Negative 60 plus 24 is, of course, yes, negative 36. And that is the elimination method. Fun! And of course, all important, who says this is right?